Good morning or good afternoon, depending wherever you are in the world today. Thank you for joining for today's webinar, where today we'll be going over GeoSLAM mining with Micromine. Today, we will be this webinar will be hosted by myself, Owen Howells of GeoSLAM. I'm the Senior Solutions Architect covering mining globally for GeoSLAM. And joining me today will be Tom Pratelli from Micromine. Here is today's agenda. First of all, I'll be going over the challenges of today's mining and why there is a need to adapt and change to suit the current climate and predictions of markets and production over time. I'll also go over about GeoSLAM, who we are, what we do, and what exactly is our product and how we could help. And that would lead into our product offering, which is under GeoSLAM Mining. And I will show how GeoSLAM has products to help overcome some of these issues that today's mining market currently faces. I'll then show how GeoSLAM Connect can process, georeference and export the data in a way that other third-party softwares will be able to accept it. Then Tom will be going over what Micromine can do. This will be a live demo and it will be showing how GeoSLAM data can be imported into the software. And Tom will then also show how he can produce production volumes, overbreak and underbreak analysis, so that's basically comparing a scan to a plan, profile control, and how to create a wireframe and a mesh. I'll also end on a nice summarization of where to find us, how to contact myself or Tom to have a one-on-one demo. GeoSLAM offer a demo in a box, and Micromine do a lot of consultation work to help mines get to where they need to get in today's climate. So just to start, this could be a whole webinar or a whole conference by itself. What is the issue currently facing mining? I've tried to summarize this the best way as I can and in quite a holistic way, which will cover a lot of bases. So here is basically the past trends in resource management over the past 100 years here, and it shows a trend on how the GDP has increased and how that's kind of affected mineral extraction. It can clearly be seen from about 1960 onwards as the GDP kind of excelled. There has been quite a large demand for more resources from the earth. So it's quite clear that as our GDP is going to increase over the next 50 to 100 years from this graph, there will be a greater need for more mineral exploration and more extraction from the earth. And that's just considering GDP. There are other drivers behind this as well. As we get into a more electrified market, the more need for battery powers, resource for creating batteries, a larger resource pot as well for our massively increasing population. You know, there's so many things that we can go over here, but this is just a quick one just to start the ball rolling, to get our minds thinking in this way. But just to focus on one mineral in particular, zinc. Zinc alone will have a raised demand for production by 35% in the next 15 years. To factor in on top of this that a lot of resources we've currently exploited and extracted are kind of the easier ore bodies, so the more accessible ore bodies. there's now a massive realization that there is a need to extract resources from areas that currently weren't viable before or weren't economically viable. Now that a lot of processes have become a lot more economically viable to run, production is a lot more efficient in some ways. We can go back into these old areas where before we couldn't extract the minerals from. So some old mine workings where perhaps the ore wasn't economically viable to extract now is economically viable. So it's up to the industry to react, as suppliers and as software providers, technology providers to the mining industry. We have to make sure we have a responsibility that our product and what we supply to the mining industry is what's needed and what will help them increase productivity and increase safety, and try and help with the digitization processes of a mine. To meet the demand of the growing mineral extraction rates, and to try and push this to become a safer and more efficient process, here are some quotes that I put together that kind of summarizes what's going on in a very, very short way. As some of you know, there's probably hundreds and thousands of quotes similar to this, but I feel this is a kind of a good way of showing what's going on. So Rio Tinto Smart Mining recently said that, data is one of the most important assets to a mine. Without the right data, wrong decisions are made and mistakes are made. Aviva in 2021 also said something similar, relating more to the market swings and the increase in operating costs. Miners who rethink and shift their focus to proactively look inward into its process and leverage technology to drive operational excellence across the entire mining value chain will be the winners of tomorrow. I find that really, really interesting. These mines, these mining companies, they are competing against each other at the end of the day to become more efficient, to have the best value. So without looking at the kind of technology that GeoSLAM provide and what Micromine could do for them, they're kind of missing the trick. I feel that a lot of us technology providers have got somewhat of a responsibility to provide this service for them, but without the actual mines being in a position to adopt this kind of technology for the good, they will lose out. So it's really important that both parties listen to each other. Deloitte also said in 2019 that core modernization seeks to solve the riddle of how companies with significant investment in legacy systems can extract more value from these systems by making them a foundation for new disruptive innovations. That really summarizes what's going on here. A lot of these operators have archaic processes for collecting data. A lot of it is just done by note taking, by looking at a surface. In this day and age, that is not good enough. We as GeoSLAM have got technology that will help in a lot of these areas. Micromine have also made a great leap recently to try and provide the best software possible to try and analyze this data coming in and to try and organize it in the best way so everybody has access to this data. So between companies like Micromine and GeoSLAM and so forth, we are trying to do a lot of the legwork for mining operators and mine owners. But we really, really feel that a lot of the advancements were made is kind of falling on deaf ears. Recently, this is changing. COVID has been a big driver by limiting the amount of footfall on the actual operations. We are seeing quite a large trend and a lot of interest going towards the management of 3D data. And GeoSLAM are in a very good place where we provide 3D data. We can capture the data very easily. And Micromine have also adapted their software to be very, very simple to use with high quality results. And that's what we will go over today in this webinar. Up till now, we've spoken a lot about external factors, what's going on in mining. So I think now's a good time to go on to discussing exactly who I represent and who GeoSLAM are. So we were founded in Nottingham in the UK, and that's where we are still based. And we are a global company, and we have a global dealer network and customer base around the whole world. So if you have any questions about how to access our technology and so forth, please let us know. We have got a large dealer network around the world and we can facilitate. But GeoSLAM makes it easy to capture and connect data from the world around us. From the built environment to the natural world, GeoSLAM technology gives people the power to connect geospatial data from some of the most difficult environments, whether they are indoor, outdoors, or underground. So GeoSLAM is the smart way to map and understand spaces. Our history. So we were responsible for the world's first SLAM-based handheld system back in 2011. So this was a pioneering algorithm that has helped organizations solve mapping challenges all over the globe. So SLAM, simultaneous localization and mapping technology. So GeoSLAM, we've got about 20 years experience in making complex problems simple. I'll go over exactly what SLAM is later on, but just to show you what our core values are, because I try and touch on this subject as we go through a bit more later. Our main core values are the speed of capture, simplicity of capture, the ability to gather business intelligence, and the automation of these steps. As we go through the slides coming on, I'd like for you to think how we tie into these. This is where we really excel. So GeoSLAM, we have the strongest SLAM algorithm going, but what is SLAM? Simultaneous localization and mapping. So SLAM is a piece of software where a device can localize itself within a map and map the area as we go. So as we use our sensor whilst walking through or driving through an environment, it will constantly recognize where it is in the world and it will map everything as it goes. So as we walk through an area, it will scan and produce a very accurate 3D point cloud as we walk through. And it does it at the speed as you walk through as well. There's no need to slow down. It'll do it as you go. So we use LiDAR. Our SLAM uses LiDAR, which is light detection and ranging. So LiDAR is basically a set of laser sensors. So our handheld units, like you see on the screen here, is a LiDAR based handheld unit, such as, so that's called the ZEB. The one on the screen there you see is the ZEB Revo, and it uses a laser sensor to generate the 3D map. LiDAR measures the distance to an object by illuminating the object using an active laser pulse. So as you walk through, imagine, although they're not visual, these lasers, they're not exactly red laser dots shooting out. You can't see them. But as you walk through it, it's constantly shooting out these lasers. And walking through the environment, it'll map everything around you and it'll localize itself. So you can continue walking through the environment and it'll always keep producing this point cloud as you go using LiDAR. The SLAM technology using GeoSLAM's product portfolio was developed by some of the smartest people on the planet. Luckily, I wasn't one of those smart people. It was created by some absolute wizards, and it's a very, very clever method of measuring an environment. The first versions of SLAM used images to help with orientation, but for laser scanning, a more frequent calculation of position is required, and continuous SLAM overcomes this limitation. With our sweep matching SLAM, scan lines are projected in all directions and enable us to deliver a highly accurate and reliable digital map. As you can see on the left there, that's a pretty cool snapshot of a scan we did. So there was a UAV, and we put one of our scanners underneath the UAV, and it scanned the outside, so there was no need for external control. You just turned it on, the drone went up in the air and went around it. 5 minutes later, we have the data to produce this image, and then we could go inside the Christ the Redeemer as well, and produce a scan of just the internal workings of that. So that's the first kind of image I've shown in this presentation of actually what our data looks like. There's some massive benefits to using SLAM. So obviously the system is completely mobile. You literally hold it in your hand, or you can put it on top of your vehicle, and you just capture as you move through the area. As you move through that whole area, it'll create a very, very accurate and dense point cloud of that area, which I'll show in the next slide now. It's over 10 times faster than the more common approaches to capturing data underground, whether it's terrestrial data, standard survey data. Critically, we do not require GPS for this to work. We're constantly scanning the environment, and it localizes itself using the environment around it. So it's a really, really cool, very clever way of being able to scan an environment. But in a mine, how does this work? It's literally as I described it. You turn the scanner on, you walk through an environment, and it captures that whole area for you. So imagine how traditional methods, you set up the tripod, you take the scan 360, you take down the tripod, you move to the next position. You literally walk through the environment and it captures it for you using SLAM. And then this is what the data looks like. It's very, very powerful data, very clean, and this is deliverable then near enough straight away. There is a process when you capture the data. You do have to post-process it. You actually run the SLAM on your computer, and it normally takes about half hour to process to create this very dense, highly accurate point cloud. As you can see in the scan, you're picking up a lot of features. You're picking up all the vent bags, picking up all the bolts on the ceiling, all the kind of infrastructures inside it as well. This is colored on intensity, so how reflective the material is we're scanning. So it's a very effective way, considering this data was captured simply by walking through this environment. It's really, really it's a kind of technology that the mining industry kind of needs to look at to kind of overcome some of the obstacles that are there in the mining industry at the moment. So it's very, very effective. Welcome to the GeoSLAM Connect viewer. So this is where a lot of the processing is done for the data. So after we've collected the data, we have to actually then run the SLAM algorithm on the data. We do have a real-time unit that does this for you at the surface. So as you scan, you see the point cloud appear. But most of the time, this isn't needed. We just need to walk through the area, and we can post-process the data using the SLAM algorithm. So our Connect viewer is a very, very simple, nice and easy software to use. And all I'm going to run through today is how to process captured data, how we georeference it, and then export it. So I'm going to start a new project. I'm going to call this by the heading code. And the workflow I'm going to use is our adjust to control workflow. We have got workflows for Deswik, Micromine, and for Vulkan as well. But for this one, we're just going to use the adjust to control workflow. And I'm going to create the project. So the project's now been created. First thing I need to do is import a scan that I did. I have a scan here that was collected with our ZEB horizon, and it's got control points in there where the user had put down the scanner using the reference plate on to survey pickup points that we know the coordinates, the true global coordinates to. So I'm going to import that data as the GeoSLAM file. Here it is. And next I'm going to upload our control points. So this will be a text file with the control points of the mine in there. What GeoSLAM have created is a way of matching the constellation of the control points. So it'll calculate the constellation from the scan of our reference points, and then the control points from here. It'll work out the constellation. So we could have hundreds and hundreds of different survey points. So we could have the whole mine's database for all their survey pickup points. And we can just import it. In this one, I've just got a few ready. There's no need to allocate which reference point is according to which control line in this text file. It will do it all automatically for us. Just going through the other options here, we have got the option to do a non-rigid or rigid transformation. I want to keep it rigid. I don't want it to expand or contract the data set. I just want to translate the data set to match with these control points. And decimation level, this is to millimeters, 10 millimeters, a point per 10 millimeters. That's fine for us as well. Next, I'm just going to name the data set. I'm just going to call this processed. And then we're ready to go. This will then import the data set. It will run the GeoSLAM, the SLAM algorithm, and it will automatically georeference the data for us using the control files we've given it, and it used our constellation mapping algorithm as well. So a lot of this is automated, and it can be done by a non-survey technician. So the processing is now complete. It's told me at the bottom here, and I'm just going to have a look at the data now as it loads in. And here's the scan. All this was captured simply by walking through it, which is incredible when you think about it. And as you can see, it's a very dense data set, and it's yet all completely georeference ready to go. So very, very happy with how this has come out. These points are just still waiting to be loaded in, as you can see there. But yeah, very good, very dense point cloud, and it's all georeference ready to go. And as you saw at the end of that, I gave it the name of the file to export it to as well. So this data set now is ready to go straight in to Micromine. So without anything further to do, I'd like to hand over to Tom Pratelli from Micromine, who will go through the various steps needed to get GeoSLAM data into Micromine. Cheers.
Hi guys, and welcome along to this webinar. Thank you, Owen, for the introduction. As what I'd like to show you is how we can take your GeoSLAM data and we can import it into Micromine. Micromine is a world-leading exploration and mine design package. And what we're going to do is show you how you can take your generated surfaces and solids or your point cloud scans and bring them into Micromine and what you can do with them. So let's just jump into the software. When you've created your scan, what you can do is then import it into Micromine. So inside of Micromine, what we can do is we can come to the survey tab, we can select the point cloud option, and in here we can inpoint your scanned information. Now, by selecting the file, we obviously support LAS or LAS formats. We also support E57s and Leica cyclone data, just to name a few. But for this data, we're going to import from our LAS file. So once you've selected the file, you then have the ability to downsample. Owen's obviously mentioned as well how you can downsample in GeoSLAM, but you can downsample on the fly here via the import, or we do have a range of different downsampling options natively inside of Micromine to downsample the point cloud from a very large, for example, 20-40 million point scan down to something a bit more manageable and a bit more less disk intensive. So we've obviously got filters to remove noise and also downsample. But for this option, we've just simply downsampled an 80 million sample point down to sort of 10% to 8 million points, so sort of decimating it. We then create a file on the fly. This will be the file where the point clouds are then stored natively in Micromine. And this is created on the fly, so we just simply add the file name there. And it's going to be attributed with automatic fields that are going to be populated on import. We obviously have the ability to import all the fields, so we can see all the attributes that are coming in here. We can change the names if we want. We can also choose to ignore any fields should we want to remove them or they not be relevant. Once we've configured that import, we're going to run the importer and we're going to select the autoload, so we're just going to run that. And once that's run, we're going to then be able to create and import the point cloud into Micromine. So it appears as a points view. So obviously it's a point cloud, and we display it as a points view. And here you can see here is the scan of about 8 million points. It displays very well inside of Micromine. We can have a look around it, so we can just have a look very quickly into it, and you can see it's a true points. We have the ability, we've obviously in here colored based on intensity, so I've already pre-configured the color set based on its intensity. We can adjust that by simply coming into the layer itself, selecting the points visibility, and I can choose to pick out certain colors on intensity. Now this is particularly helpful for some clients that like to have or already might have their surveyed points as a particular color. Typically survey points might be a very bright color it allows us to pick them out, so we can target those sort of colors very quickly there via this sort of intensity slider. Then we can isolate particular areas, or for example isolate any areas that might be sort of erroneous or not required. Obviously, once we've imported that data, we can have a look at it, check that it's imported in the correct location, check that it's displaying correctly. We can come through, we can very easily create a section just to walk through and see what the data is looking like. So for example, in here, if we just have a look into the section, we can move through the plane and just come through and see if the scan has worked successfully. Are we seeing any internal features that we may otherwise not wanted? So I'm just going to open it out a little bit here. So here's a 10-meter swath as we just walk through our underground network, and you can see it looks like it's performing correctly. You can actually zoom right into the points, and we can actually see whether and how successful our scan has been. You can particularly notice, for example, if there are any obstacles or if any machinery or any vehicles have been involved in the scan that we might need to come in and remove it with any noise filtering or so on. Once we've done that and evaluated that, we can then start to move on to creating a wireframe. Okay guys, let's talk about how we can then take your data, your scan data, bring it into Micromine, create a point cloud view, and from that point cloud we can create wireframe surfaces and solids from that data. So let's show you. Inside of Micromine, we've already seen that we created a point cloud and we've been able to color based on the intensity. We can then take that information from the point cloud and using our point cloud to solid tool, which is located in the survey point cloud to solid tool, we can select the point cloud file that we've already imported. We can have a look at some of the surface control options that we have. So for example, we have the ability to control the triangular edge length, which just basically allows us to prevent the wireframe from going too far beyond the existing points. We can also downsample and make sure that we're not creating duplicate triangular faces where there are a lot of points. We also have the ability to control webbing. So webbing allows us to effectively control areas in a point cloud where there are voids and how we deal with voids or any lack of information, for example, that we might have incurred from sort of some shadows or some areas that just didn't scan well. So with the webbing tool, we can control that. We can choose to web over it, or if particularly we're not interested in doing that, we can slide down and make sure those areas that we might not want to web over or cover over aren't covered. We can also simplify the wireframe to ensure that the wireframe isn't larger than it needs to be. So areas where there is a lot of data or points inhabiting very similar spaces, we can make sure the surface wireframe created is as simplistic as it needs to be. But we can also discard any volumes. So for example, some satellite areas are very small volumes, or particularly at the edges of these scans where we have just some noise. We can make sure these little areas are removed and tidied up. Once we've configured those settings, we can then come into Micromine. Micromine stores all its surfaces and solids inside of a wireframe type. We can then give it a name. Once we've selected that, we can select the auto load button. So once we run that surface meshing algorithm, it's going to generate a wireframe surface or solid for us. I've run this already. It took about just over 2 minutes to generate a surface that looks like so. You can see actually this is actually a solid. So if we just came in here, if we selected it and hover over it, it's going to tell us the attributes. We can see this is actually a solid because it has a volume. And let's just quickly come in and evaluate how well that surface has been created. So here is the surface. Here is the point scan. So you can see it's fairly accurately created a surface from that. Let's come into section and just evaluate that a little bit further. So here we are in the drawn section. You can see in the pink sort of magenta color, we can see the actual wireframe surface. Here is the other point clouds, and you can see it's rather accurately created that wireframe around them. Let's just go for a little walk through the tunnel. We can open the actual swath through a little bit further so we can see more information. And you can see basically with the pink magenta line representing the wireframe surface. Actually, the wireframe surface is very well fitted to the point cloud data. Okay, there aren't any areas where we don't fit that data very well. Let's just come out of the section. And overall, that's a very well created surface that is actually a volume. And you can see in particular areas just towards the edges where we maybe have come out of the scanned area, we can increase the webbing to make sure that's sort of covered up if we wanted to, or we could include that in another scan and merge the two. So overall, a very good result and very quick and easy to create surfaces and solids from a point cloud. Now that we've generated a wireframe, we do with those wireframes once we've got them into Micromine. So really opening up the Micromine package and showing you what great tools and features we have for taking your data further and making meaningful interpretations based on your scans, and showing you what we can do with a world-leading exploration mine planning package such as Micromine. So once your scan has been imported in, and we've generated a wireframe like in this case, we can start evaluating our actual surveyed material versus against what we planned. So in this example here, we have a scan of one of our declines that we've just extracted. And what we want to do is just go and evaluate and look back and reconcile this against what we actually plan to do. So once you've created those wireframes in Micromine, we can then go a little bit further and start making meaningful interpretations. So here's an existing example of one of the declines that we have. And what we're going to do now is we're going to evaluate that decline versus what we actually plan to produce. So here is the original planned decline. You can see it's quite a bit different. Often is the case we have planned to construct this, but this is what we actually produced. So you can see via this, you can see they're quite a bit different. If we come to draw them, or come to see them in section, you can see how different they are. So just having a look at this in section. So just having a look at this in section, you can see they're quite a bit different. Overall, they're very similar in a very similar location, but ultimately, when we've actually come to extracting the material, what we've planned versus what actually is achieved is quite a bit different. So we have a lot of tools in Micromine to help and allow us to evaluate how different it was and what the difference between the design and the actual is, so we can reconcile the differences. One of the most powerful tools, and one that our clients particularly appreciate, is the ability to compare these two wireframes and to meaningfully evaluate them. So using the wireframe compare wireframing tools, we can come in and we can select both of those wireframes. So we've got our planned decline versus our actual decline. And what we're going to do is we're going to store back the difference attribute to an attribute called distance. So this will basically act as an attribute where we can store the difference between one wireframe to another, and we can display that across the wireframe. So let's have a look at this in action. So once we've run that, we can come into the actual decline, and we can choose to color based on that distance attribute. So let's just color based on that. And what that's going to provide us with is a detailed color mapping. If we bring up the legend here, we can see actually how far we've deviated away from our planned as-built. And particular areas in here, if you come to your legend, anything with a sort of orangey to red color is more than a meter away from where we actually plan to extract the material. So if I turn the plan back on again, you can see there's particular areas over here that where we've significantly deviated away from where we were sort of planning that material. And that can be fairly interesting to try and understand this and trying to evaluate this. For example, if we've extracted a lot more material, we can come in and run some reports on the amounts of sort of overbreak and burden amount of material that we've chosen to come and extract. So we can just sort of reconcile between what we plan to do and what we actually achieved. So there's a lot of great applications here for looking at overbreak and underbreak. In this scenario, we've been particularly interested in looking at overbreak analysis, but the application of comparing these as-built wireframes versus our actual plan here is also applicable to something like convergence, where we might want to monitor slope or any movement within tunnels, and this would provide us details as to if there's been any particular movement with any structures or anything like that. If we're doing a pretty consistent scanning, we could monitor material movement like this and be able to display whether a particular slope or a particular face, for that matter, has moved or has any sort of convergence has been applied to it. Let's move on and let's just have a look at how we can physically report out that information. So here is the exact same decline that we have been looking at. Instead of displaying it on distance, all I have produced is a physical display of where we have had overbreak material, so I can reconcile what we've planned as to and evaluate it as to what we actually planned versus what was actually built. So I've identified, and using the wireframe Boolean options, so we can interactively cut wireframes from each other. I've created two separate solids. So here is the original as-built surface, and that has only been created where inside of the planned area, so only inside of this planned area. Now, any material outside of that has been identified as overbreak or overburden material. And what I can do is I can save this as a separate wireframe, and I can start quantifying it. So I can say, hey, this amount of material wasn't planned for. Potentially we've over extracted material, and this is the amount of material we have extracted. So I can very easily come into the reporting tools, and in Micromine we can generate a volumetric report and a tonnage report based on these wireframes. I've already saved these two separate wireframes in a set. I've configured the density item. We could be storing the density to the wireframe, and I can very easily run a report that will tell me instantly. We can see here the volumetric totals. I can see the volumetric of my overbreak material and the total tonnage versus my planned material. So I can very quickly reconcile the material that we hadn't planned to extract, but we actually have encountered. Okay guys, what I'd like to finally do is talk a little bit more about what we can do and how we can report on the wireframes that we created from the scan data imported in from GeoSLAM. So just really showing you what else is possible with this data once we have got it into Micromine. Ultimately, once we've imported these wireframes into Micromine, the world's really your oyster. We can look at scheduling, we can look at ring design, we can look at development design, we can reconcile material, we could use this material for face mapping, structural mapping, and so on. So there's a whole load of different applications, not even mentioning grade control or anything like that. So let's just talk a little bit about some of the nearer applications. So one of the things I'd like to talk about is how we can easily slice this information, and this is applicable in the underground environment or even sort of open pits. So we're going to slice maybe this existing as-built out into 30-meter slides and have a look at the volume. We could use that information to maybe assess what sort of materials we might need, or reconcile some sort of production data that we might have. We can also look at generating plans and example strings that we can export to various other formats such as DWG, DXFs, and so on. So let's just quickly have a look. So in Micromine we have the same decline that we have been looking at, and it's fairly simple to affect some slicing information very simply by coming into wireframing and selecting the option to create mining blocks or to slice the wireframe. So we can slice it any way we want. So in this instance, what I've done is I've picked my wireframe, I've told it to output to a file called slice30, and I'm going to slice based on an orthogonal view looking north, and we're going to take 30-meter spaces based on the lowest corner value, which is that. So once I press run on this, what effectively is going to happen is we're going to slice this solid up, and we slice it into 30-meter swaths. Okay, so this is something I have already done before. Let's just go open those existing swaths. So here we go. I've also colored it just a little bit differently so you can see those different views. Here we have those 30-meter slices of the tunnel. We've sliced vertically here, but we could also take smaller swaths. We could take horizontal if we want independent surfaces, and we've actually created cut solids here. So let's just turn some of these off and turn the visibility off. We've actually, as you can see here, we've actually closed it at the end so we can get a volumetric solid. So once these have been generated, I have actually chosen to display the labels displaying all their volumetric tonnages. We could use these for scheduling. I've got some examples where I've actually used this as-built design, and we could start planning, for example, highly accurate ring design. I've got one example here, so let's just have a look and let's just quickly jump into a ring design that I've created earlier. You can see we can take this information and we can make a ring, create a ring design for underground drilling that is effectively modeled on your as-built design. So just another example of how we can use this information and feed it and make our mines a lot smarter. So really, that is just a good example of how we can use the data. One other thing I know a lot of people are interested in is maybe taking this information and slicing it up into maybe some strings or some solids. So we can very easily do that just in the viewer now and here. For example, we have this one wireframe here. If I simply come into the wireframing tools, we can have a look at creating a silhouette in whatever direction we want. So for example, if we had our production crew and we wanted to export to them a production string of our existing developments, I can easily come into a plan view. I select the option from strings, generate strings. I'm going to select the option silhouette. I'm going to pick our wireframe. If I right click now, watch out what happens. It's just going to generate a wireframe, a string around that, and just project it to a 0 elevation. So there we go, very nice and easy. We could then take that string, we've obviously got it saved as a separate string file. We could then take that information, export it out to DXF or DWG or whatever the field crew might be using. Okay, so here really ends what I wanted to show you guys. I really appreciate you guys attending this joint webinar today. If there are any further questions, or if you would have any more information, would like any more information about Micromine, please don't hesitate to get in touch. Thank you, guys.
Thanks very much for that, Tom. Really appreciate going over some really useful material we've gone over there. So just to conclude now, I just wanted to summarize the offering that we make. The GeoSLAM products, we are made for demanding environments. We are easy and fast to use. We're efficient. We've got an excellent after-sales support team. We are pushing a lot for our products to be used with a heavy aspect on safety, and we can be used at any site at any time. We do offer a demo in the box. We do offer a demo in the box option for you, which could be useful if somebody just wants a demo of our software, of our hardware and our software to see how our units perform on site. So please let us know if you're interested in that. Also, Micromine, they're more than willing to do localized demos to show how their software could help you guys really achieve the digitization goals that a lot of mines are striving to, trying to get to these days. GeoSLAM have got a lot of customers around the world. I'm sure Micromine have also got as many customers. We're confident in this field, and we have got the resources to help you guys out. So please join us on our social media. We do post a lot on our LinkedIn and Twitter pages. But we'd like to go on to the questions now. We have had a couple of really good questions come in. One of the first questions has come in asking about our adjust to control method, how we georeference. And we would ask, can a non-rigid adjust to control be used if they can't close the loop? So when we capture data using our handheld units, we try and ask the customer to close the loop, so to end where they start. But we have got a way of processing this if you cannot return to the starting location. We call this open loop. And adjust to control can help with this. Yes, the non-rigid processing of this will help with open loop. So adjust to control, a non-rigid method, will help the SLAM in some areas. If there's enough control and you use the normal SLAM capture techniques, there shouldn't be a need to do this. Another question has come in regarding adjust to control again. I think georeferencing of the data is a hot topic. Asking about the reference points.
if one of the 4 points is the starting point from back of the car, that was also recorded. So to summarize this question, it's asking, can the software identify reference points that aren't to be used? And the answer is yes. If there is a point that's clearly outside of the constellation matching, and it's recognized that, we can detect which one is the most erroneous point, and we will look to try and process it without using that point. So we can take that in. And I see there's a couple of questions here for you then, Tom. Are you available to answer these?
Hey, Owen, yeah, thank you for that. And yep, sure, I'll just quickly answer these. So the first question, and just read it out loud. Hi, when you have imported the last file into a wireframe, did you have any problems regarding the triangulation? How you managed this before calculating the volume? Is there a way to easily remove points such as ducts and mobile equipment? This is a really great question, and it's something we have looked at, and it's something we have experienced. Now, GeoSLAM is producing some very nice data, and to be honest, the data that has been produced has been nice and cleaned, and we didn't really have much ducting, if any. There have been some scans with some equipment, specifically humans and cars. When we came to creating wireframes from these, those points were ignored, and our surface meshing algorithm didn't factor those in. So there's two real aspects to this. There is noise filtering within Micromine, and we have noise filtering, and just quickly listing the types. We've got outlier radial, and median absolute deviation, which would hopefully remove anything like ducting or any sort of noise that we might experience. A lot of the time, I think a lot of the artifacts are removed in GeoSLAM, but also our surface meshing algorithm is such that these artifacts tend to also be removed and not considered as part of the bigger picture of the wireframe of the decline or whatever underground development you have. So hopefully that answers your question. The second question is very similar. So let's just read this second question. The second question is, in Micromine, by which parameters can we remove maximum noise and get the smoothest yet real solid model? Yep, that's really kind of a question about noise filtering within Micromine. Again, Owen did talk about processing within GeoSLAM. We can also process and remove noise within Micromine. As I've just said, we do have the ability to remove noise via several noise filters. So depending on the environment and depending on the data, we can use noise filters such as outlier statistical, outlier radial, and median absolute deviation, which tend to pretty much remove all sort of noise that we might have in our data, and just allows us to remove any artifacts that potentially aren't there and create a much better wireframe. We also, and I did touch upon it briefly in the demonstration, we also have downsampling, and we can effectively take very high density point clouds and create downsample them, but without losing that resolution that is key to the surface creation. Okay, so guys, I hope that answers the questions. Please do keep them coming. I know Owen has listed our email, so please do feel free to get back in touch. I'll hand back over to you, Owen.
Yeah, cheers, Tom. We will be sending out an email straight away after this summarising the webinar. We'll also have the contact details on that and how to proceed if you're interested in the demo from either side of us. Thank you very much for attending. I hope this has been informative, and please let us know if we can help you any further. Thank you very much.